Aujourd'hui, on a le plaisir d'accueillir Caroline Martel, qui est à l'Institut des sciences de la Terre d'Orléans, que vous connaissez. Elle a déjà, par exemple, elle avait fait une conférence lors de la journée soufrière que Jean-Christophe et Arnaud avaient organisée il y a quelques mois. Donc aujourd'hui, elle va nous parler de l'observation pétrologique des volcans. C'est une spécialiste de pétrologie expérimentale appliquée à la volcanologie. Voilà. Qu'est-ce que je peux dire d'autre? Le directeur de recherche au CNRS à Orléans, voilà. Et certains d'entre vous la connaissent à travers ses activités de directrice de programme à l'Institut. La connaissent en bien ou en mal, bien sûr.
Merci. So thank you, Mark. Asked me to talk in English, so talk in English. So I'm happy to have the opportunity to present my current work. It's a great pleasure for me. And I will start with a short CV, and especially because I'm now an external member of your scientific committee for the theme of natural hazards. I'm also a member of the SNOV, the National Service of the Volcanological Observatory, since 2014. I've been leading the ISTO Orléans committee on seismic, volcanic and gravitary hazards for about 5 years. Now I'm a member of the CNRS Section 18 committee. And I've been also leading the magma team at the ISTO. We have only 5 teams. And I will switch soon for the assistant direction of the ISTO lab. Concerning the scientific responsibilities, I've been leading or co-leading or participating at a number of French projects on magma deformation, lava dome explosivity, eruption dynamics on the Antilles volcanoes, on magmatic processes at Merapi, and I've also been actively participating to the European Vuelco project on volcanic unrest in Europe and Latin America. So my scientific interest concerns the domain of volcanology, and I aim to understand the magmatic processes that decipher eruption dynamics. And my favorite approach is experimental petrology. And of course, this is for the holy grail of predicting volcanic eruptions for evidence purposes of crisis management. So predicting volcanic eruptions, this implies answering at least that 3 questions: when the eruption will occur, how it will happen, so how explosive it will be, and where or to which extent it will go. So for the when question, I would say that the precursory signals that of magma arrival that we can have through seismology, geodesy, or gas measurements are quite useful. However, it is sometimes difficult to discriminate between different things through this method. For instance, in seismology, it's sometimes difficult to interpret the signals in terms of cold rock fracturing or gas percolation or magma movement. For deformation, it's because of the inversion process that requires assumption on the reservoir geometry. It is also sometimes difficult to have a really high resolution of the source localization, and it is also difficult to follow the magma moving upwards to the surface. And for gas measurements, then if we want to have evidence of magma arrival, then we have to be sure that these are magmatic gases. So there's still some work to do, and it's good in a way. And for the question of how explosive, or the question of the eruption dynamics, then we really require to understand the deep magma processes and to find some links or relationships between these deep magma processes and the precursory signals and the eruption dynamics. So there are relationships between these three things to find to really be able to answer the question of how will be the eruption. So what do I mean by eruption dynamics? Quickly. I'm talking about magmatic eruptions, so not about phreatic eruption that do not involve juvenile magma. So we can put these magmatic eruptions into two categories, the dome-related eruptions and the Plinian eruptions. The dome-related eruptions are characterized by the growth of a dome and its destruction into more or less violent nuées ardentes. Mera P-type are mildly explosive block and ash flows that are generally channeled into valleys and can give thick deposits. In contrast, the Pelion-type nuées ardentes are surges or blasts that are commonly overflowing valleys and that generally lead to very thin deposits of 10 to 20 centimeters maximum. And then the Plinian eruptions are mostly pumice and ash fallouts, but they have a much broader impact in terms of geography. And they can be really thick deposits, and their main problems in towns is that they can collapse roofs of houses. What about the deep magma processes, and what can we learn from petrology? So by deep magma processes, I mean the conditions of the magma storage, so the pressure, the depth, the temperature of the magma, and the content of dissolved gases. And the magma ascent conditions are more or less related to ascent rates and paths. So in the reservoir, the process are basically equilibrium crystallization that gives phenocryst in a silica, in a volatile bearing silicate melt, and this equilibrium can be sometimes perturbed by magma arrival from underneath. And then when the magma is sent in the volcanic conduit, then we have degazing and crystallization, mostly in disequilibrium, crystallization of macrolides, and this concerns the volatile bearing silicate melt here, because the phenocrysts are mostly staying as they were in the magma chamber. And then eventually we can have fragmentation of the whole magma into fine particles and ash. So I won't go further into the magma storage conditions, but they can be determined experimentally by simulating crystallization in the magma chamber under controlled condition of pressure, temperature, and the different gas fugicities, and this is performed in pressure vessels. So I've been worked on that magma storage determination for nearly 20 years now, so determining the storage of several volcanoes in the Antilles, like Mont Pelé in Martinique, or Soufrière in Guadeloupe, in Dominica, the Merapi in Indonesia, Chêne des Puys and the Pavin in the French Massif Central, and Tungurahua and Cotopaxi in Ecuador. So these magma storage conditions are determined experimentally, are really interesting to confront to the determination via the geophysical methods. But they can't give any information on the geometry of the magma chamber and on the size of the magma chamber. However, these are really key input for the study of the syneruptive conditions in the volcanic conduit. So when the magma starts to rise in the volcanic conduit, then it can degas, and it's degassing because here with decompression, you can put less and less water dissolved in the melt. So when the magma is ascending, then it will cross this water solubility curve, here determined for rhyolite at a given temperature, and then all the excess water has to exsolve as bubbles. So on this scheme, the magma is ascending, then it crosses the volatile saturation curve, bubbles nucleate, they grow, they can develop a permeability network, and if there is sufficient time and if the conditions are favorable, then you can lose this gas in the surrounding rocks or around the domes, and then this volatile poor magma is erupting effusively as dome grows, then can further be distracted into nuage ardente. However, if you don't let enough time or the conditions are not the right one for losing gas, then the magma keeps its bubbles, and because it's with the bubbles, the growing bubbles, the density of the bulk magma is always decreasing, then it can really accelerate and reach a fragmentation process or level and erupt as Plinian eruptions. So to better understand the conditions of this degassing process, we can simulate experimentally the decompression and the degassing through time series of isothermal decompression experiments with rapid crunch to keep the bubbles, their shape and their fraction as they are. And then we can decompress continuously or step by step, or instantaneously decompress and have dwells at final pressures. So this is also performed in pressure vessels, and you have here images of this time series as a function of time for a rhyolitic melt, decompressed from 200 MPa to 5 MPa. And with these images, we are measuring the bubble fraction, the bubble number density, and the bubble size. With all these time series, then we can end up with a sort of lifetime of a magmatic foam, that is, the conditions and the time required for a magmatic foam to collapse or to lose all its bubbles. And so this is a diagram with the degassing duration, here in hour. The bulk viscosity, that means the viscosity of the volatile bearing melt plus the bubbles at equilibrium. And it defines 3 domains. The green domains were bubbles are still nucleating and growing, so that the measured porosity, the phi here, is lower than the calculated porosity at equilibrium. A domain in white of equilibrium degazing, where the measured and calculated porosities equals. And we can also observe in this domain a domain where the bubbles are not really coalescing, and a domain of extensive coalescence. And finally, in red, a domain of outgassing for the long duration and the low viscosities, with, for the really long duration, the foam collapse, where the bubbles are really no more in the samples. And then we've tested this lifetime of foam, of magmatic foam with natural products. So you have some pumices from Montpellier and Pinatubo, and knowing their degazing duration, or the time of eruption, and calculating their bulk viscosity, they indeed fall in the domain of equilibrium degazing and extensive coalescence. And the clasts from the surge of Montpellier, 1902, is indeed falling in the domain of outgassing and severe foam collapse, and they do not contain more than 30 volume% of bubbles anymore. So this is for more or less static foam. There's no big stress on that samples. They are not deformed, they are in capsules, and we are just decompressing. But of course, in real life, there can be some high stresses and high strains, and that's why we are also deforming bubbly melts in Patterson-type deformation press, that is a pressure vessel that is able to deform in torsion or coaxial. And this has also the possibility with these volumometers of measuring or bringing fluid pressure at the top of the sample here, or here if we take a real sample, and then measuring the fluid pressure at the bottom of the samples. So this means for us that when both fluid pressures equilibrate, then the samples became permeable. And that's what we can see on that diagram, the function of stress and strain, deformation. They are deformed at different shear rates, but the arrows, the black arrows here, is when the sample became permeable, where the two fluid pressures equilibrate in the machine. And then we recover the samples, post-mortem samples, and then we noticed that the permeability of the sample was not induced by bubble coalescence to a gas channel that would connect the top and the bottom of the samples, but they became permeable through extensive fractures. And of course, it's also because the starting bubbly melt is not that rich in bubble. So under strain, they were becoming permeable by opening fractures. And depending on the shear rate of the experiments, then we noticed that these fractures were different, and they were big and not numerous at low strain rates, and they became small but really numerous at high rates, high strain rates, so that it tells an evolution of the permeability from the center of a conduit towards the margin of a conduit. So this was the first kind of study we did with that samples, but now, of course, we plan to increase the bubble content of the sample so that bubble could coalesce and make their own gas channels. And of course, we will add crystals for more realistic magma. Now, so the acidic magma degassed, and it can also crystallize. And it's crystallizing because here you can see that with decompression here, the magma, the red arrows at one temperature, is crossing the liquidus of the rhyolite. So the liquidus defines on the right the domain of totally liquid to a domain on the left with liquid plus crystals. And so you can see that there's the equivalence between pressure and water content following the water solubility laws. So the driving force for the crystallization of macrolides in the volcanic conduit is due to decompression-induced meltwater depletion. From the shape of the liquidus, we can also notice that the difference between the liquidus temperature and the real temperature of the magma is smaller at high pressure, so deep, than it is at low pressure. And this is what we call the effective undercooling. So effective because we are not really cooling the magma. The magma is considered isothermal. So what is changing is the temperature of the liquidus. That's why we say effective undercooling. But this undercooling is much higher, close to the surface. And undercooling is directly controlling crystallization in terms of crystal content, crystal size, and crystal shape. And indeed, from the experiments, we can see that at high pressure here, so low effective undercooling, the crystals are rather few, they are large in size, and they are tabular in shape. And these are plagioclase macrolides, and they are calcium rich. In contrast, for the low pressure above, so high effective undercoolings, then we have lots of small dendritic crystals, and they are rather sodium rich. In between, the characteristics are intermediate, and we have skeletal shapes. So there's a mean here from the macrolide characteristics to retrieve their crystallization conditions in terms of undercooling and then in terms of pressure, and we will see also decompression rate. So the preceding image here, that was experiments. Now just have a look at the natural samples with the example of Montpellier. So in the Merapi type volcanoes flows, then we can see that these macrolides, here you have, it's 10 micron scale bar. The macrolides are rather large, and they are tabular in shape. In contrast, the one from the Pelen type surges, like the May 8, 1902, they are much more numerous, they are more tiny, and they have skeletal shape. For the Plinian, in the Plinian pumices, most of the matrix are microlide free. So there are indeed crystallization difference in terms of undercooling, or they crystallize under different undercoolings, so on different pressure. And that's what we will try to constrain through experiments. I won't go into details here, just to explain the principle. So these are decompression experiments designed for crystallization. That one, the one that I call post-decompression crystallization, the melt is rapidly decompressed, and then there is time series dwells at the final pressures as a function of time. These are the pictures we recover after each experiment, and in these images, I'm measuring the number density of the crystals, their fraction, their size, and their composition. And what we can see from this post-decompression crystallization is that there are lots of macrolides. They are small, they are skeletal to dendritic, and they are rich in sodium. In contrast, for experiments performed with continuous decompression, no dwell at final pressure, we quench the experiments at final pressure, and these are continuous decompression that can last up to 40 days. Then we can see that the macrolides here are fewer, they are larger in size, they are tabular to skeletal in shape, and their compositions cover a larger range that reflect the fact that they are crystallizing at different pressure during decompression. So using this kind of experiments, and before I will show you how it compares with the natural product, just with two examples. So these are the experimental samples. The first one on the left is an instantaneous decompression followed by 4 days at 5 MPa, so it's decompressed from 200 MPa. And that's the natural pyroclast from the May 8, 1902. And it compares quite nicely so that these decompression conditions and this decompression path may be realistic conditions for the crystallization of the macrolides in the May 1902 pyroclasts. On the right, it's an experimental continuous decompression from 200 MPa to 5 MPa also, but during 17 days. And here is the one class of the block and ash flows of the 1929 eruption of Montpellier. And also it compares quite well. The crystals are also tabular, and they compare in number densities and fraction. So also these are realistic conditions for the crystallization of these macrolides in this product. So now combining these decompression experiments on crystallization and degassing, we are able to propose some eruptive scenario at Montpellier, starting from the magma chamber here, so about 875 degrees C to 200 MPa, so about 7 kilometer depth, and a melt with 6% of water. If we consider first the premises from the Plinian eruptions, then from the experiments, we could say that the magma ascends from the reservoir very rapidly, let's say hours, because this gives time for degassing at equilibrium, all the water that has to exsolve as bubbles did. But there was no time or the conditions were not good for losing these bubbles. So they stay within the melt. And because of this rapid ascent, of course, we have no time for crystallization. And this led to overpressure or a rapidly ascending magma that eventually fragment in the conduit, highly explosively, to give this Plinian eruption. In contrast, for the Merapi type nuardons, so the block and ash flow, the mildly explosive ones, then the magma must have ascended very slowly, at least within more than 5 days. And then this leads to a continuous equilibrium degassing, and we have even time to lose the bubbles in the surround rocks or anywhere. And also, there's a continuous crystallization, like we've seen in the experiments. So that the magma became permeable. At the end, there's no more gas over pressure, and it can erupt effusively or mildly explosively as flows. And in between, the case of the surges of the 1902 surges, and then in this case, I propose that the magma ascend quite rapidly. I mean, more than hours, but less than 3 days. So let's say 1 to 3 days. So this gives time for equilibrium degassing with a permeable magma that is losing its bubbles, but it's too short for crystallization during ascent. And then, in fact, crystallization occurs at dome level because the magma stopped. And it stopped for less than 4 days, during which macrolides crystallize extensively. And because it is an extensive crystallization, and because these macrolides do not contain any water in their structures, the water from the melt is pushed back to less and less residual melt, so that at the end, bubbles have to exsolve. And this triggers a new nucleation event at low pressure, at dome level. And of course, because it's low pressure, the bubbles will need really place to grow, but they don't have that place. We are in a confined medium within the dome. And also, under these low pressure temperature conditions, we can exsolve a silica phase that goes preferentially within pores, so that is filling pores somehow. So we probably end up with really high gas over pressures that eventually overcome the strength of the magma, leading to these highly explosive surges. So what about the next eruption of Montpellier? So what we have now, it's sort of petrological monitoring. I mean, we know from the macrolides characteristics the eruption dynamics. And we found some relationships between the magma ascent rate and path, the degassing and the crystallization processes, and in fine, the eruption style, or the eruptive style. What we need now for sort of prediction of the next eruption would be magma ascent rates and detection of possible shallow storage, like cryptodomes, like during the 8 May 1902, the magma stopped at dome level, or at least it was seen the day before at the surface. So we know the magma is really at the top of or very shallow. So this could be given, of course, via the geophysical monitoring, seismology, geodesy, maybe radar interferometry, etc., or imaging techniques, seismic or muon tomography. There's still some work to do. Because, of course, if we could know the magma ascent rates and its path, then we could predict the eruption dynamics from what we've seen in the experiment. So it's all, of course, kind of ideal, but that's the idea. So that was a work performed in details on Mount Pelée, but now we could extend this kind of studies on other volcanoes, because each volcanic system is unique in terms of composition, pressure, temperature, gas content, and of course the relationships between the deep magma processes and the eruption dynamics have to be determined for each case. So now it's a work in progress for MERAPI through the framework of the MERAPI INER. We have a very fine field study. We know the pre-eruptive conditions. We are currently performing decompression experiments, and there is an active geophysical monitoring on that volcano. We could do it also for the Teide, Tenerife, with the additional interest that it's a different geodynamical context. It's no more island arc subduction. It's intraplate volcanism. And this leads to very different magma compositions, alkaline, phonolite, etc. So it's also something that we plan to do in the next few years. And I think it would also be worth trying on Soufrière of Guadeloupe. Now, to optimize this kind of petrological monitoring, I have several objectives in the future. I would like to compile experimental data from different volcanoes into empirical models that could predict the syneruptive degassing and crystallization, and in fine the eruption dynamics, as a function of the magma composition, so ranging from calc-alkaline to alkaline magmas and from basalts to rhyolites, and then as a function of pressure, temperature, and decompression rate. And for that, it will be easier with our new in-situ simulation and analysis that replaces the time-consuming time series experiments. So this is realized in the framework of the Equipex Planex at ISTO. The aim is to equip high pressure and temperature vessels with windows that are transparent to different spectroscopic radiation. So of course the visible just with an optical fiber, but then we could observe the degassing and the crystallization processes, but also with the in situ Raman and infrared spectroscopy, then we could monitor the degassing during decompression, and with the X-ray we could better monitor crystallization. So this is in progress. And my second objective would be to replace these empirical models of bubble and macrolite growth by numerical models. And for that, we need to know what is controlling the processes, whether it's diffusion or viscosity or something else. But this would really broaden the use of these experiments and these syneruptive processes for the volcanological community. And finally, last slide, this perspective of collaboration to go on and studying the syneruptive processes and the eruption dynamics. So we definitely need field geologists, good field geologists, that can link a volcanic deposit to an eruptive dynamism. And I've put a nasty sentence in small letters. In France, there are few field geologists in the domain of volcanology. And soon they will better handle fishing rods than hammers. So it's a tension point where we really have to make sure that this expertise is not lost now. We need experimentalists to realistically simulate the deep magma processes. We need, of course, modelers to generate generic models of syneruptive T-gassing and crystallization. We need geophysicists and geochemists to validate the petrologically determined ascent rates and paths before it can be used for the interpretation of past eruptions. And of course, this requires active volcanic targets. And in one sentence, this is just to say that there is really space to set up multidisciplinary projects on volcanic unrest and eruption. I also forgot to write down here that we would also need some social scientists to deal with risk assessment. Thank you for your attention.
J'ai le micro. Qui veut commencer à poser des questions? Pas tous en même temps.
Yes, just to what mechanism do you attribute the change in microlite composition with the degree of undercooling?
It just depends on the meltwater content, so on pressure somehow. We know that the plagioclase composition is first dependent on meltwater content. So at low pressure, low water content, then you have more sodic compositions.
And how well do they match with the natural samples? Did you check that?
It depends on what you are looking at. Of course, if it's the kind of block and ash flows that obviously ascend continuously, you have any kind of composition and even zoning within these tiny macrolites. But for the May 8, 1902, they crystallize obviously at a shallow level and all there. And here the compositions are really constrained or few range, and they're really matching what we can obtain through equilibrium, phase equilibrium.
Yeah, I was wondering, are there clear differences that you expect between the plumbing system of a volcano that will have an ascent rate that allows it to erupt within a few hours and volcanoes who have 5 days? That's the first part of the question. And second, and attached, is considering that these processes, what makes them very different is only a difference in days. What are the perspectives for actually predicting, using techniques to predict practically?
So the first question
the first question was okay, there are volcanoes that will produce catastrophes because the ascent rate is very, very rapid, and others where it takes days. From a geological point of view, both are very rapid, but are there differences in the conduits in the plumbing system?
You mean on geometrically?
Yeah. Are these volcanoes different, or can it happen at any given volcano?
I would say it could happen in any. We are talking about silica-rich volcanoes with silica-rich magmas, but yeah, I would say any kind of conduit geometry, length, size. It's just a question of pressure, hydrothermal pressure on that. So, and indeed, Montpellier can alternate both styles within nearly the same eruption. For instance, the P1 eruption started with that surge, where the magma is ascending, I would say about 1 to 3 days, and then stop. And just after, the Plinian eruption was triggered. So it's not depending on the volcanic system itself. It's really depending on what is coming underneath, probably. Is it pushing fast, or Do we have big overpressures in the magma chamber? The triggering mechanism, it's not clear to me what is really triggering the eruption.
So then,
but
how can you predict what? Because your approach is
post-mortem.
Mortem. It's not predicting.
That's why it's for prediction. I think the prediction will be made by geophysical methods. It's a monitoring in the sense that it's predicting the eruptive dynamics, the eruptive style, but it's not predicting when it will arrive. And I think only geophysical or imaging methods could provide numbers of ascent rates, but not petrology.
Caroline, I was wondering, just in your decompression experiments, how does the charge actually expand?
It depends on the chosen final pressure, but it can be multiplied by...
So you have some kind of confining medium that allows it to expand?
Yeah. The samples is confined in a gold capsules commonly.
Yeah.
But then the gold capsules is big enough to allow degassing and the volume of degassing. The volume it's just the water that goes out that needs place. So
your sample actually degasses. It's not that the whole thing doesn't expand closed, but it actually loses gas. Is that right?
Yeah, well, the bubbles dissolves within the sample, within the capsule.
Okay, and then that gas leaves the capsule.
In some case, with the one that I call the foam collapse, then the gases leaves the melt samples and goes at the top of the capsule. Okay. But it's no more trapped within the melt.
Okay,
but it can live trapped in it.
The reason I was asking is that I guess the pressure trajectory that you show us is the one that you impose from outside the capsule. Yeah. And what we want to know is what's the pressure trajectory inside the capsule. And those are not going to be the same, or at least they'll be influenced by how the thing is allowed to expand. So that was the reason for my question.
Yeah, but the real the real processes, I think it's not the intrinsic. It's not because it's degassing that.
No, I understand. It's the pressure, but it's the pressure inside the capsule that you need to know, and you're telling us the one that's outside. And so I was just wondering how the thing actually managed to expand, so that you can deduce the internal one from the external one.
No, that's the same.
Only if they're in pressure equilibrium, but if the thing's trying to expand, then they're not going to be exactly the same.
It's trying to reach the equilibrium with a delay, but there is space and time for that.
D'autres questions?
Yes, you mentioned your detailed studies on post-mortem studies. How best can you integrate your expertise and your techniques in an observatory context to look at the onset of the eruption? If we have the chance to have early eruptive tephra, what will you look for in the products that can give you some insights on what might be happening?
Oh, in any case, I think that's maybe like the question of Mathilde. There's no way to predict something looking at the eruptive product. The prediction will be a combination with the geophysical methods that would give me the ascent rate. But it could be useful just to interpret past eruption, but not for the prediction of the next one.
I'm not talking so much about prediction, but if you have early eruptive tephra, for example, the Mount St. Helens eruption, you had tephra produced by phreatic eruptions initially a few months before, and then as the magma rose, you had more and more perhaps a juvenile content in the tephra. How can you use petrology in an observatory context to understand what is going on? Not to say exactly what will happen, but Are we having magma participating? Is it ascending fast or not? Can you?
Yeah, from this, you could tell how it.
What would you do in an observatory? What would you?
I think it's the same kind of study. You need to choose the right composition, to do decompression experiments, and to deduce the ascent rates or where it stopped from the macrolite characteristics.
Toute question? I can just slightly change subject. So there is a big question on the water content of the moon, lunar mantle, and there are volcanic glaciers at the surface of the moon. There is lava fountaining, and I was just curious to know whether you can use the kind of approach you have developed to put some constraints on the initial water content of the source of these melts. Did you think to that, or? Because you have, or it can be an end member of your experiments with a melt with no water. So there are other volatiles, but not much. And so I was wondering whether there was something to do with that.
If you have some crystals, then you could go back to the water content of the melt at the time of crystallization.
Yeah, but there is no.
If you have no crystal, just.
I was stupidly wondering how you could have lava fontaining for a melt which has no volatile, for instance. Yeah, but not much the same. So, well, what is if we can determine what the minimum amount of volatile we know, or the degassing, the depth from which the magma should come, this kind of thing.
Small amounts of CO2 should be enough to exsolve explosively.
What? Because you observe small 100 micron glass spherules everywhere deposited over large areas. Stupid question. D'autres questions avant d'aller au buffet? Non? Ok. Merci encore.
Merci.